Alright, this is problem 6.7 out of Griffiths Quantum Mechanics, Introduction to Quantum Mechanics textbook. If you wouldn't mind, please like the video and subscribe if you find this helpful. Okay, let's get to it. Consider two particles of mass 1 and m1 and m2 in one dimension that interacts via potential that depends on only the distance between the particles. And they give us the Hamiltonian. And they also show us what the translation operator does to such a system. Part A says, so that the translation operator can be written as such, where P is P1 plus P2, which is the total momentum. And here I just copied down what we kind of already had. So before we tackle the two particles, I think it's important to talk a little bit about if you had just one particle, because it's essentially the same idea. So what we basically have here is a translation operator acting on a wave function. This is just essentially the definition of the translation operator. You can actually write this as a Taylor series. Okay. So for a Taylor series, just in general, 1 over n factorial, and I'll write it like this: the nth derivative of whatever function that we have, x minus a to the nth power. Okay. Now, what we can do is we can go ahead and expand this as a Taylor series. And if we do that, let's see, we'll get an infinite sum from n equals 0 to infinity. 1 over n factorial, and we'll do this about x equals 0, so minus a to the n, and the power is what's left. And the nth derivative. Now remember that the momentum operator is minus I h bar d by dx, or d by dx equals minus I over h bar p hat. And just trust me, I know that there's a difference between a second derivative and raising something to the second power, but it works out okay. We can now plug this into here. Okay. So we have our infinite sum. That doesn't change. And now I'll have, I'm sorry, that should be a positive because we divided that over and then moved it up. Sorry about that. Minus IA over h bar, the momentum operator to the nth power, and then you just have your wave function. And this series is e to the whatever is in here. If this was just an x, then it would be e to the x. But we obviously have more, so it's minus I a p hat over h bar. And that's why we can ultimately write, since this was equal to, we can ultimately say that our translation operator is e to the minus IA p hat over h bar. So essentially what we're now doing is we're now just doing this for two situations. So we're going to have a sum, just as before, n equals 0 to infinity, 1 over n factorial. The only difference here is we'll call this momentum 1. This is for the first particle. Okay. Or we can say that this is psi of, I guess, x1. No, that should be x1 comma x2. We're going to use a different variable, so m equals 0 instead of n, but fundamentally the same idea. And this would be p2 over h bar to the nth power. So, once again, you will get, and you get a psi of x1 comma x2. And we had our translation operator acting on this, is equal to e to the minus I a, this stuff, e to the minus I a p2 h bar, and then our wave function. And we can see that our translation operator can be written as, I'm going to make this in 1e, and I'll factor out a minus I a over h bar p1 plus p2. And the question, it was defined that p1 plus p2 is just equal to p. So we showed that our translation operator can just be written as e to the minus I a p h bar, which is what they wanted us to show. Now let's see. So that was part A. What part B wants is it wants us to show that for the total system, the momentum is conserved. Okay, so I'm going to start with this. H prime, our Hamiltonian in the translated state. This T dagger, HT. So when you do this to our Hamiltonian, you get your H prime, which is the translated Hamiltonian. But we know what that is. This is just going to be our untranslated Hamiltonian. And we can justify this, I think, pretty solidly. First, what is our potential? It's the absolute value of x1 minus x2. That's how it's defined in the problem. So let's do a translation operator acting on our potential. This would then just be equal to v of x1 minus a minus x2 minus a, which is obviously v of x1 minus a minus x2 plus a. And we can see the a's cancel, and we simply, so what this is telling us is that under this transformation, our potential remains the same. So the potential is invariant, which is half of our Hamiltonian. The other part of our Hamiltonian, because let's remember that this is our Hamiltonian. I think we just argued successfully that that part is invariant. And hopefully, from a previous problem, we showed that p prime equals p. So this part is also invariant. If you'd like the justification for this, the last, maybe it wasn't the last one, but one of the last videos, we actually showed this as a homework problem. So I think this statement is completely justified. Okay. We also want to make note that t dagger equals t dagger t, which is just 1. In other words, it's unitary. We also showed this in a previous homework problem. So if you'd like to see this justification, I think it was 6.2. So why did I mention that? Well, we can use these last two parts of the equation here. T dagger ht equals h. And hopefully you see that I can write this as t dagger ht equals th. In other words, I just have just did this. But above, we know that this is equal to 1. So this is simply ht equals th, or ht minus th equals 0, or the commutation relation between the Hamiltonian and the translation operator is 0. In other words, the Hamiltonian and our translation operator commute. Okay, now why do we care about that? Well, let's take a very small a, delta. We know what that's equal to. Instead of a, we'll put delta. And if we expand this with the Taylor series, this will be 1 minus I delta h bar p plus some other terms. But remember, delta is very small. So in these additional terms, we're going to get smaller numbers raised to the higher power. And these become less significant. And again, this is just the Taylor series for E. Or if you just went up to and expanded these guys to whichever term. But obviously, instead of A, we're using delta, as I said before. Well, we just showed that the Hamiltonian and translation operator commute. But because of how we expanded it, we can replace a translation operator with this Taylor series expansion. And the Hamiltonian surely commutes with 1. That's just 1. That's just a number. And the second term will have some constants, minus I delta over h bar. Those can be factored outside your commutator relation. And our commutator, h bar p, momentum, is equal to 0 from here. Okay, cool. So we see that the Hamiltonian and momentum operator commute. That's important because of a property we have, which says the time derivative of an expectation value of some operator is equal to I over h bar, the commutation relation of the Hamiltonian with that operator, plus dq dt. In this case, the operator we're using is momentum. And hopefully you can see where we're going with this. And if not, that's okay. I'll try to explain it to the best of my ability. And we're replacing Q with P. Well, momentum is not a function of time, so it's safe to say that this is in fact zero. There's no time dependence. We just showed that this is zero in the earlier step, which means d by dt of our expectation value of momentum is zero. And this means that momentum is conserved in this system. Okay. It's supposed to look a little nicer. So hopefully that made sense. I try to go into some of the details on why we did certain things. So hopefully it's not just giving you the solution, but maybe helping explain the concepts to you as well. If this helped, please like the video and subscribe. I'd appreciate it. Thank you.